Hello and welcome back to part 2 of our confidence intervals in chapter 10. So we left off before going over the rough confidence interval. Now we're going to another confidence interval formula, and this is a better formula to use because it'll be a little bit more accurate in determining confidence intervals that are not 95%. So first thing we're going to talk about is here's the better formula for when alpha of 1 minus alpha 100% confidence interval for mu when sigma is known. I want to start by saying that when we have alpha and confidence intervals, or just confidence percents, alpha and confidence, they share a natural, we'll call it a correlation. They share a natural bond together. If you have 95% confidence in something, that is a 5% alpha level. These two always together are going to sum to 100% or 1, a value of 1. They are inversely related to each other. So if you had 90% confidence, then you would have a 10% alpha level, and so on and so forth. So when we're looking for a more accurate confidence interval, our formula is going to be x bar plus or minus z of 1 minus alpha over 2, right? So look at this as like a z percentile. So you need your 1 minus alpha over 2. So if you had, an alpha level, say you had alpha level 0.05, right? This would be z of 1 minus 0.05 over 2. 0.05 divided by 2 is 0.025. 1 minus 0.025 is 0.975. So you're looking for the z percentile of 975 in the back of the book. When you look this up, you'll get a value of 1.96. One of those things, I think it'll just make your life easier. It happens all the time because we use alpha at 0.05 a lot. One of those just numbers you might want to commit to memory. So moving back to the formula, x bar plus or minus our z1 of subscript 1 minus alpha over 2 times the standard deviation or sigma divided by the square root of n. This is also known as the standard error of x. Note that when the standard sigma over square root of n is the standard error of the mean, like I just said. So moving on to common levels of confidence. Once again, if you have a confidence level of 1 minus alpha, confidence level of 0.9, your alpha level is 0.10, and it has a z value of 1.645. 95% confidence, 5% alpha level, 1.96, so on and so forth. Just a visual representation of it. These z values, once again, are not a bad thing to memorize. So if you had a 90%, if you wanted to have a 90% confidence interval for mu, and you were given you took a simple random sample of 712 people, standard deviation of 40, and your x bar is 183, and you wanted to derive a 90% confidence interval, what would you do? So for a 90% confidence interval, your formula is going to be mu is going to equal x bar plus or minus z1 minus alpha over 2 times standard deviation or sigma over n. So now we just plug in the values that we know. We know our x bar is 183 plus or minus our z of 1 minus alpha over 2. Now remember, since our 90% confidence interval, our alpha is going to be 0.1 over 2. So it'd be z of 1 minus 0.1 over 2, which if you go back to the other slide, at 90% confidence interval, our alpha level, or z value, is going to be 1.645. 1.645 times standard deviation of 40 over the square root of 712, which when we work all of this out, you're going to get 183 plus or minus 2.5, which then gives you 180.5 to 185.5, and you would say that you are 90% confident that the true value of mu falls between this range. And that's how you do the confidence interval for at 90%. So let's do one at 95% confidence interval. So same random sample, same X bar, everything's the same. This time we're just using a confidence interval of 95%. So again, our formula is going to be X bar. It's going to equal, I'm sorry, not equal. Let's see if I can do this relatively quickly. Never mind, we'll just keep going. So X bar plus or minus Z of 1 minus your alpha over 2. In this case, your alpha is going to be 0.05 times your standard deviation sigma over square root of n. So you can have your 183 plus or minus 1.96 times 40 over the square root of 712. You're going to be left with 183 plus or minus 2.9. So it's going to be 180.1 to 185.9. And this is saying you are 95% confident that the true value of mu is between these values. Same thing for a 99% confidence interval. I'm going to go a little quicker through this one. So I'm not going to write the formula because we've seen it before. You're going to get your 183 plus or minus 2.576, and if you're curious where that value, once again, head back here at 95% or 99% confidence, 1% alpha. Your z value is going to be 2.576 times 40 over the square root of 712. So you're going to get 183 plus or minus 3.9, which is 179.1 to 186.9. And this is saying you are 99% confident that the true value of mu is between these values. So all that we did here is it kind of laid out in a little nicer handwriting than what I do. So here's your confidence level, and then your illustrated confidence level, and then your confidence length. Confidence length is just the upper confidence level minus your lower confidence level. One thing you should notice is that as you increase your confidence, right, as you get more confident, if you're 99% confident something's going to happen, you better be really sure that's going to happen, right? You're 99% positive something's going to be there. If you notice, as you get more confident, your confidence interval expands, right? Because it wants to capture that true value of mu, and in order to be more confident, your range is going to open up, right? And that's where we get this CL length. As you see, it gets larger as you increase your confidence level. Moving on to 10.3, sample size requirements. So to derive a confidence interval for mu with a margin of error m, to study many individuals, this is how many individuals do you need, or the sample size required for that confidence interval. And our sample size, n equals 1 minus alpha over 2, which you can always revert back to that chart earlier to determine those values, times sigma over the margin of error, all that squared. So now, if we were to move on and do an example problem of this, so suppose we have a variable with s equals 15, which s, if you remember, is for a sample, it's also our standard deviation, and want a 95% confidence interval. Note that alpha is 0.05, so our 0.05 alpha level will give you a z value of 1.96. So say if you wanted a margin of error, say your margin of error equals 5, we want to determine our sample size of n now. Remember, n is going to equal our z of 1 minus alpha over 2 times standard deviation over the margin of error squared. Plug the information we know into the formula. This is going to be 1.96 times 15 divided by 5, all this squared, which then you're going to get a value of 34.6. Or, since we're dealing with n, sample size, individual people, you can't have 0.6 of a person, so you round that up to the nearest whole person, so you say 35 people. Let's see if you had a margin of error of 2.5. What would your n size then be? Same thing. If we're solving for n, at 2.5, our confidence is still the same at 95% confidence, so you'd say 1.96 times 15 divided by the margin of error of 2.5, all squared, is equal to 138.3, or we're going to round it up to 139 individuals needed for that. Say you only wanted a margin of error of 1, and you wanted to figure out how many people would you need, so you only had a margin of error of 1. So you put 1.96 times 15 divided by 1 squared, and you would get a value of 864.4, or 865. So as you can see, as you want to decrease the margin of error in your study, the more people you need. Remember, in statistics, more people normally always the better answer. You always want more people. So the more people you have, the smaller margin of error you will also have. So the smaller margins of error require larger sample sizes. So in 10.4, we start talking about the relationship between hypothesis testing and confidence intervals, right? So last chapter, all about hypothesis testing and whether or not we reject a null or we fail to reject a null. So a two-sided test will reject a null hypothesis at an alpha level of significance when the value of the null mu falls outside the 1 minus alpha 100% confidence interval. So remember, if you're 100% confident on something, your alpha level is going to be 0, right? Because they share this relationship. But if you're 100% confident, the true value of mu has to be in there. We are stating it has to be in there. When we say 99% confident, we're still saying there's a 1% chance it won't be there. But if you're saying there's 100, mu has to be in there. And if mu were to fall outside the range at 100% confidence interval, then you have to reject the null hypothesis. So there's between confidence interval and hypothesis testing. So we have an illustrated example where reject mu equals, so a null hypothesis equals 180, alpha level 0.05. Because when he falls outside the range of the 95% confidence interval, that's why we reject mu. You will retain the null hypothesis at 180 at 0.01 because the 99% confidence interval does capture mu at 180. So here's the illustrated example of this, right? If we were 95% confident shown here for the sampling distribution of x, you see it would fall just outside the line, so you get to reject the null hypothesis. And then here's the confidence interval, 99% confidence interval. So that is your illustrated example showing it. Remember, you want to reject the null hypothesis always. By rejecting null hypothesis, it means your sampling distribution falls outside of the critical values, the critical range of mu, and that is why we're able to reject it, because what you have found is statistically significant compared to what is accepted or known, or the null. All right, so that ends confidence intervals. Once again, it's relatively short. It's a very short week, very short chapter. Goes over very quickly. Once again, it's fairly straightforward. Once again, if you have any questions at all, always feel free to contact me, email me, or set up an appointment during office hours. All right, have a great time and be safe.